sequence. Now question is how to predict lives for in case. Again, of course, you need a SN curve, and if the SN curve is available like MMPDS or ES2 data with a different KT, well and good. Now again, as expected, you may not get. You may get a KT, but you wanted a KT different thing, which curve will not be there. Then you have to do interpolation and thing, provided it is within that KT. Suppose you have a KT is equal to 1 and you have KT equal to 1.3 or 2 is there, but you need KT equal to 3. Then there is an issue in extrapolation. But if you SN curve is available for KT is equal to 1, smooth 1 and KT is equal to 2, but your problem is 1.5, then you can do interpolate. Or you have to go into conservative way. You take KT, but it's too much, so you may not meet the life objective. So to get a KT 1.5, there is another way. Again, interpolation is the issue. I will come to that. There's a very important aspect on that. You cannot do the interpolate, though we are in one point of time I have told you can do interpolation as long as within the things, but in this case when coming to the KT it's not allowed. I'll tell you why. Now the one way is this: you calculate the new time histories for the component. You can say whether KTN or KTG. You know this is the stress concentration factor for that structure having stress concentration or discontinuity. In that case, whatever applied stress is there, you multiply that much and use SN curve, which is as I will use smooth, because you already amplified the magnitude. I mean stress range you have changed from this is actual applied stress for which you are supposed to find the life. Provided if you have SN curve is available for KT of say 2, then directly you know the S is this much, S max is this much, your KT SN curve KT is there, substitute you find the life. But if it's not there, you have only SN curve is equal to 1 is available. In that case, you amplified that much times using whatever KT you are getting. But the problem is you will get very conservative. So in usually generally you calculate what KT is equal to maximum localized to nominal, and this takes care of KT. Okay, then you have SN curve available for KT equal to 1. Then with maximum local stress, where you found suppose 3.1 is the KT, your life will be coming this big dotted line. Okay, but actually your structure is experiencing fatigue strength thing. It's a metal experience, but this is analytical. Suppose for 100 in this case, your life is say 5 into 10 to the 5 as per the too much scale. Now actually if you test with 100 with actual the same configuration, we will get up to 10 to the 6. Again we don't bother about this KF, because with KT 0.3.1 calculation you are happy with 5.105 is fine. It's coming below. Okay, you wanted to have the life should not be more than 10 to the 5. Your 100 megapascal, it is coming 5 into 10 to the 4 is coming, not 5, no, 5 into 10 to the 4. But your objective is it should be less, then don't worry. But in reality at 100 you will be getting 10 to the 6. Again, if you are trying to correlate with theoretical and experiment, theoretically life is saying 4.5, but the experiment you are saying 10 to 6. Then how do you correlate with that? In the vast one, you are taken care of correction factor, knockdown factor, whatever possible. Still, you will not able to do unless you take care of KF. The issue is, the problem is, even the plate with circular hole, you are having applied stress with the nominal stress. Local stress, I was telling you, sigma and epsilon is generally represent the local stress strain curve. Though you may not have a plastic deformed, the KT, so you have a 3, right? On the previous example is a 3.1. If your S max is 100, your local stress become 300, right? If you take, but your yield stress is 290. So obviously there will be a plastic deformation. The KT calculation you have to do statically. You are taking KT into SA. This is the amplitude you are taking. So that's why you are getting higher KT. But due to the plastic deformation, you have a cyclic, your stress distribution takes place, your stress amplitude comes down. That's your life is more theoretical speaking. Okay, so this is what KT you calculate the elastic behavior. This is called elastic stress constant factor or theoretical stress constant factor, that is based on the static analysis. But actual behavior, what material when subjected to cyclic loading, it goes to hysteresis leave, stress distribution, it go to plastic deformation, then unloading it comes down. If you still look, your stress amplitude reduces. That is the reason why you get a higher life during test compared to the